let's try this example, doing the inverse Laplace transform on this longer piece. You may want to pause the video here and try to do it yourself and see if you can do it on your own. And then if not, come back and watch and see how it works. So notice first of all that we have three distinct terms that we can split up, because remember the Laplace transform is a linear transformation, which means we can split it up and take one piece at a time, and we can also pull out constants. So let me do that first. Let me break this up and take this first term, and while I'm at it, I'm going to pull the 5 out outside of the Laplace transform. So then it would be 1 over s minus 6. Then we have minus, the same thing with the next one, gives us 6 times the Laplace transform of 1 over s squared plus 9. Now, let me pause on this one and mention that looking at this, you might be thinking ahead and thinking how this looks like either a sine or a cosine. And if this top happened to be 3, we might leave it there to make it more convenient. But if it's not exactly 3, it might be just more convenient to pull out the 6 and deal with this constant on its own rather than trying to adjust a 6. It's easier to pull the 6 out and then adjust a 1. And then for the next one, I'm going to pull out the 3 and the 2. So that would be 3 halves, and then the Laplace transform of 1 over s squared plus 4s plus 5. So there's a little bit more work we need to do before we can do the inverse Laplace transforms. Now this first one, we don't have to do anything to, because looking at the table, that's exactly e to the 6t, right? If that's s minus a, where a is 6, it looks exactly like e to the 6t. So that one we don't have to do anything to. It's pretty much done. This next one is close. We have s squared plus 9 in the denominator, which means it's either going to be sine or cosine. If there was an s in the numerator, we would try to make it cosine. Since there's not, we're going to make it sine. And in order to make that work, we have s squared plus b squared in the bottom, so b is going to be 3. So we want to have a 3 up here. Since we don't right now, what we're going to do is multiply by a 3 inside and multiply by a 1/3 outside. So this is kind of what we did in the last couple examples, except kind of skipped a couple of steps and jumped straight to the result, where we'd multiply by 1/3 and 3 inside and then pull the 1/3 out, because that's the one we don't want. So now this one and this one are both in a form that we can immediately take the inverse Laplace transform with. The next one is not quite so simple. Here we have s squared plus 4s plus 5, which is not one of the forms that we are familiar with, not one of the forms that shows up on our table. So instead, we need to do something to that. And what we need to do is we need to complete the square, because what we'll get when we complete the square is something like s minus a squared plus b, more or less. So we need to go back and complete the square. We've done this on a couple examples recently, but just to review that again, let's show that process. And let me do this off to the side here. So we have s squared plus 4s plus 5. To complete the square, we need to have s squared plus 4s plus something, and then if we add that on, we need to also subtract it, and then we have the plus 5 as before. So we have s squared plus 4s plus 5. We're going to add and subtract something, and the thing we want to add and subtract is chosen carefully to make this part be a perfect square. And so just to review, if that's going to be a perfect square, this is 2 times something, and this is that same thing squared. If you expand it out, you have something like s plus or minus a squared. That would be s squared plus 2as plus a squared, right? So if this is 2a, that means a has to be 2, and so then you find a squared, which is also 4. So the punchline to all this is that to complete the square, just look at what number you have here, divide it in half, and square that, and that's what you need to put here. So take 4, divide it in half, and square it, and that tells you what your mystery number is. So we're going to add and subtract a 4 here, and then by doing so, this part in parentheses is guaranteed to be a perfect square. This one is s plus 2 squared, and then we can simplify the minus 4 and the plus 5 to be plus 1. So after completing the square, let me do this on another line. We have everything we had before, and then we have plus 3 halves times the Laplace transform of 1 over s plus 2 squared plus 1. Now it still doesn't look super simple, but if you look back at your Laplace transform table, this should look somewhat familiar. It should look like the sine or cosine with the exponential modifier on it. So where normally we'd have s squared plus b squared, now we have s minus a squared plus b squared. Now because there's no s in the numerator, it's not the cosine, it's the sine instead. So what this looks like is it looks like, I'll just remind you, that e to the at times sine of bt gives you b over s minus a squared plus b squared. And so for matching up pieces, a would be negative 2, right? So s minus a gives you s plus 2. And then b would be 1, so that b squared is 1. Now conveniently, that also shows up in the numerator, so we don't have to do any more adjustments with constants, which kind of makes our life a little bit easier here at the end of the problem. So having done all that, we're finally ready to write down our final answer. So this would be the first part, this 1 over s minus 6 is e to the 6t, we mentioned that earlier. This right here is the sine of 3t, and with that we write down our final answer. We have 5 e to the 6t minus 6 times 1/3 is 2 sine of 3t plus 3 halves, and then we have e to the at sine of bt, where a is negative 2 and b is 1. So there's our final answer at the end of the whole problem. So there's a little bit of complicated algebra here. We had to be able to complete the square and sort of modify constants as needed to get the right form. But as long as you're careful and you take each piece one step at a time, and you can do this algebra, you should be able to do problems like this.